Now we would like to start defining some properties that we commonly use to describe fluid systems. So first off, we have pressure, and pressure equals, denoted by the symbol P, equals to the force divided by area. And this is the amount of normal force that is exerted per area. So imagine if you have a surface area here, and there is a force exerted on that area in the perpendicular what we call the normal direction of that area, then this would have an associated pressure value. Now, pressure has units of pascals or PA, and you might notice that force, since force has units of newtons and area has units of meters squared, this is equivalent to the unit of pascals. So you might sometimes see pressure expressed in units of pascals or newtons per meter squared. Just know that these two are basically talking about the same thing. So next we have density, and density is defined as the mass concentration of fluid per volume. It is represented by the Greek symbol rho, um, and has units of kilograms per meter cubed. Now, density equals to mass divided by volume of the fluid. So this talks about how much fluid mass is concentrated within the volume that the fluid takes up. So keep in mind that fluids still are made up of many molecules, and based on this, we can see that density can actually vary depending on the temperature and the pressure of the fluid. So we know that temperature is a form of expression of how much energy is inside the system. So if we have higher temperature, then we know that there is higher energy associated with the molecules, and higher energy molecules will move faster and want to expand and have an increase in volume. Thus, if we have higher temperature, your volume you will want to expand, increase, and your density would be lower. On the other hand, pressure talks about the compression of your fluid. So if we have high pressure, meaning that the molecules are being compressed together, then we will have a decrease in volume, and our density will actually increase in this case because we have a decrease in volume while having the same amount of mass being concentrated within that decreased volume. So density can actually vary depending on the temperature and the pressure. Now, this ties into another assumption that we like to make, and that is called the incompressible fluid assumption. So, an incompressible fluid is essentially a fluid where the density experiences negligible changes with pressure changes. So, we're saying that for our incompressible fluid here, no matter how much we change the pressure, there will be so little density change that we will assume the density change to be zero. Now, this approximation is typically done for liquids, and if we look at liquids, it really is the case where if we if we just change the pressure normally, there wouldn't be too much change within the density of the liquid. This is very different from gases, where any kind of pressure changes would have a significant density change. Now, this incompressible fluid assumption is pretty useful and convenient because when we're analyzing fluid systems, um, having density being one less changing factor that we need to account for simplifies the calculations a lot. So if there is a case where we're analyzing the flow of a liquid, we can say that the density has no change at all throughout the system, and we will assume it as an incompressible fluid. It's important to know that this does not mean that liquids have zero density change. It will still experience density change. We're just saying that the density change is so little that we can ignore it. Now we can move on to specific weight. So specific weight is essentially the force weight of fluid per unit volume. It is denoted by the Greek letter gamma, and it has units of newtons per meter cubed. In terms of the formula, the specific weight equals to the density of your fluid times the gravitational acceleration, which is approximately 9.8 meters per second squared. Now, if you recall, um, weight is defined as mass times gravity, essentially the gravitational acceleration experienced by an object. So the specific weight tells you the gravitational force. Sorry, I meant gravitational force earlier. It tells you the gravitational force associated with your fluid here. And now you commonly hear of what we call atmospheric pressure. So since we know that fluid can exert pressure, um, when you're standing outside under the atmosphere, there will be a certain pressure exerted onto you. This also applies to basically any kind of fluid that is open to the atmosphere. So the surface of a lake, for example, will have pressure acting on that surface due to the air within the atmosphere. Now, pressure can actually change based on altitude. So when we talk about standard atmospheric pressure, we are talking about the pressure experienced at the sea level. Now this is denoted by pressure ATM, and this has an approximate value of 101,300 pascals. Now you may know that this value is actually pretty large, and you might know that when we start analyzing fluid systems, that pressure values, if we use the unit of pascals, pressure values will typically have very large magnitudes, a very large order of magnitudes. So Pascal, even though it's the SI unit, it actually is a very small measurement unit for pressure. So that's why you frequently see uh, values written in units of kilopascals or megapascals. Just something to keep in mind. Now we have specific gravity. And specific gravity is the ratio of the density of the fluid in comparison to the density of water. And this is denoted by Sg here. Sg equals to, the specific gravity equals to density of our fluid divided by the density of water. Now the density of water, we know that, again, density changes based on pressure and temperature. So the density of water is typically taken to be at the standard atmospheric pressure and a temperature of 4 degrees Celsius. And under these conditions, the density of water is typically around 1,000 kilograms per meter cubed. This parameter is also called relative density, and it basically just tells you, gives you information of the density of a fluid. Now, since this value is the ratio between densities, there are no units of specific gravity. Specific gravity is a dimensionless parameter with no units. So for an example, if we say a fluid here, let's just say a random fluid here, let's just say mercury. How about that? Mercury has an approximate specific gravity of around 13.6. Remember, no units, it's dimensionless. Then this is basically saying that so we're talking about mercury, basically saying that the density of mercury here is equal to 13,600 kilograms per meter cubed. Specific gravity is basically just a way to represent the relative density of a fluid. And lastly, we have vapor pressure. And vapor pressure is defined as the pressure that is exerted by a vapor that is in phase equilibrium with its liquid and is denoted by P subscript V, where V is for vapor. Now, this parameter is actually not too often discussed when talking about the mechanics of fluid by itself. This is typically ties more into thermodynamic and energy analysis of fluids. But it's still something important to keep in the back of your mind. It basically says that if I have a container here, let's say this container has water, and we know that liquid water, can evaporate into small gas water vapor molecules, then the pressure exerted by these gas molecules is basically the vapor pressure.